Hello and welcome to this video. In this video here, I'd like to present some of our most recent research on localization of speech and audio in reverberant environments. And this work was presented earlier this year at ICASP 2016. So first of all, an introduction to the work here. So direction of arrival or the direction of arrival of audio and speech is very useful for many different applications. And that could, for example, be in surveillance systems, but also in beamforming applications. But reverberation is well known to have a detrimental impact on the estimation of the direction of arrival, since most existing estimators do not explicitly account for it. And this is actually a quite serious problem for the above mentioned applications. So what we propose here is a reverb robust DOA estimator, which is based on a simple reverb model. So if we, for example, take a look at a room here where we have a sound source which is playing back, and then we have a number of microphones over here which are receiving and recording the sound, then we do not only receive the direct sound from the sound source, but we also receive all the reflections from the walls. So if we look here on the right hand side on the impulse response from the sound source to the microphones, then we can see that it contains both the direct sound component but also early reflected sounds, as well as a dense tail here of late reflections. So the model that we consider for the DOA estimation here is that we have a direct path sound component, then we have some early reflections, and then we consider the rest as noise. So let's go into a bit more details about the signal model. So if we assume that we have capital K microphones that records n samples each, then we get the model here in 1. So we have a long vector y of all our observations, and this long vector here is constituted by a number of subvectors y1 up to yk, and each of these subvectors contains n samples from one microphone. And all these observations here can then be modeled as a sum of a desired signal S plus some noise V. Then we have some further model specifications here to facilitate the estimation, and that is, first of all, that the noise is assumed to be white Gaussian noise. And then we assume that the desired signal is quasi-periodic. This may seem like a strict assumption, but actually this is a very general assumption that might not give us any limitations. Then finally we have that we have a uniform finally we have that we have a uniform linear array structure, but again what we present here can be generalized to other array structures, so it's not a big limitation. Okay, so since we assumed that our signal is periodic, then we can model our clean desired signal as in 2 here. So our clean desired signal is given by a sum of 2L harmonically related sinusoids, and since they are harmonically related, their frequencies are integer multiples of the fundamental frequency omega 0, and then each harmonic here has a complex amplitude alpha L. And then an important observation here. So this model here actually contains also the more widely used broadband model, since it's a special case of 2 if we set the fundamental frequency omega 0 to be equal to 2 pi divided by n, where n is the number of samples, and L to be equal to n divided by 2 rounded down. About the array model. So we assume that the source of interest is in the far field of the array. So for a uniform linear array, we can then model the time difference of arrival of source R between microphone 1 and K as in 4 here. So the time difference of arrival is equal to the microphone number times the distance between the microphones times sine to the angle of the source R divided by c, the sound speed. This can be written more compactly as k times eta R. So on the next slide here, I'll then present the complete signal model, which we can come up with based on all the earlier assumptions and models I introduced. So the observation of multiple early reflections in noise can be modeled as in 5. So our observations Y here are modeled as a sum of capital R early reflections, and each early reflection here is modeled by a steering matrix H here, which is dependent on the time difference of arrival of reflection R as well as the fundamental frequency. And alpha here is then the complex amplitudes of the harmonics for that particular reflection, plus the noise here. The estimation problem that we are left with is then to find eta, the vector eta here from our observations. And the vector eta here is then the time differences of arrival of all the early reflections. So by estimating not only the time difference of arrival of the direct path component, but also all the early reflections, then we hope to reduce the estimation error and the bias of the time difference of arrival of the direct path component. And to achieve this, we use an iterative procedure. So first of all, we consider a modified observed signal model like in 6 here. So we have a modified observation vector yr, which is given by the observation vector y minus all the reflections that we are not interested in. So basically yr here should approximately only contain one of the early reflections. This then suggests that we can estimate the time difference of arrival and the amplitudes of the rth early reflection by minimizing the squared 2 norm between the modified observation vector yr and the steering matrix and amplitudes for the rth reflection that we're interested in. So if we minimize this cost function here with respect to eta r and alpha r, then we should be able to estimate the unknown time difference of arrival and amplitudes of the rth reflection. This enables an iterative DOA estimation procedure, which we have termed the reverberation robust nonlinear least squares method, or RNLS. So the algorithm can be seen on this slide here. So in the first step, we assume that we only have one early reflection, and then we estimate the angle eta1 and the amplitudes of this early reflection from the modified signal model y1, which is just equal to the original observation. Then in the second step, we subtract this first early reflection from our observation, and then we estimate the angle or the time difference of arrival of the second reflection and the amplitudes of that second reflection from this modified signal vector. Then we go back, re-estimate eta1 and alpha1 from y1, and we iterate like this until we have practical convergence. In the third step, we then include yet another reflection. We iteratively estimate the angle or the time difference. Then in the third step, we include yet another reflection in our model, and then we iteratively estimate the time differences of arrival and amplitudes of these different early reflections. Then we continue like this until we have all the early reflections that we're interested in, and we have practical convergence. Of course, in practice, we won't know what the number of early reflections is, so we can either estimate it using a model selection criteria, or we can fix it to a certain value. In our experimental results, we evaluated our method here on a real speech source. So we used 4 seconds of female speech, which was synthesized spatially using a room impulse response generator. The pitch and the model order that we need in our estimator were estimated using an LS estimator that were proposed earlier. In the setup here, we choose a number of early reflections equal to 4. The reverberation time T60 was 0.3 seconds, and we had 4 microphones. If we then look at the root mean squared errors here in our table, then we can see that the robust NLS method here outperforms both the NLS method, where we only assume one direct path component, but also the SRP FAT method here, which is maybe the state-of-the-art source localization method for reverberant scenarios. Thank you so much for watching this video.